Can you share your screen? Yes. Okay, welcome back everyone. So our next speaker is Bernstein, who will be talking about maximizing as base point.
Hi everyone. Hi everyone. Thanks for having me. I posted a link to my website, and you can find the slides that I posted. So if you want to flick through at your own pace, you can see that. Also, please feel free to interrupt me with questions. Deliberately made my talk, it should be about 20 minutes, so there should be time for interruptions. So I'm very interested in the kind of this modern machine learning paradigm where we have a training set. We have a massively over-parameterized neural net. Not only can the neural net interpolate the training data, but it can interpolate the data in lots of different ways. The driving question that I'm going to be interested in is primarily why do neural networks generalize? Why does deep learning generalize even when non-generalizing functions exist in the function space? And I'm also going to be interested in and touch upon what does this have to do with information theory? I'm going to cut to the chase. I'm just going to give you the punchline of the talk. The punchline of this talk is a new perspective on generalization theory that builds on lots of old ideas. But the idea is that if we have a space of interpolating classifiers, we can think of them, they interpolate our training data. We can think of them as forming an ensemble. So any neural architecture implies an ensemble of interpolating classifiers. In classical machine learning, if you have an ensemble, the typical thing that you would do to make a prediction is to aggregate over the ensemble. For instance, you might take a majority vote. But the key idea of this talk is that if a neural network is such an expressive classifier, it can directly fit the majority vote of its own ensemble. So if you have an ensemble of very weak classifiers, that wouldn't be possible. But since neural networks are very expressive, they can fit their own majority vote. And the idea is that actually, that's the classifier you want to return when you do deep learning. And the argument we're going to make in this talk is that implicitly, that is what is happening when you're doing deep learning. The way you set up the objective function, the way you train your network, you actually do this thing. This perspective is kind of nice. One of the reasons it's nice is that it allows us to apply theoretical results. So if we're dealing with ensembles, then we can apply information theoretic results to understand generalization. We're dealing with taking majority votes, so we can apply voting theory to understand that. And finally, we're going to apply some ideas from complex geometry to understand when when taking majorities doesn't take you outside of the function space, like when some tools in geometry can tell us about when that's possible. So the key idea is actually not a new idea. This idea of individual classifiers approximating ensembles goes back to at least this paper in 2001, where the authors defined something called a base point machine. A base point machine is a single classifier which is expressive enough to approximate an ensemble directly. So really what we're doing is we're porting this idea to deep learning. It was proposed in the context of kernel methods. So we call this thing the neural network base point machine correspondence. And so just to spell it out a bit more graphically, we have this thing, given a training set, we can construct, theoretically, we can construct an ensemble of interpolators. And we could consider passing an input into all of this ensemble and then aggregating, for instance, by taking a majority vote. This is a nice thing to think about because we have good theoretical results for understanding ensembles of classifiers. It's a bad thing because actually constructing such an ensemble in practice is very expensive. On the other hand, on the right-hand side, we can think about a single large margin neural network. The key here is that it's trained to large margin. This is going to be a key detail. you know, the bad thing here is that we don't have good theoretical understanding. This is what we want to develop. But the good thing is this is actually what's used in practice. This is what we care about. If you train a machine learning model in practice, you return a single classifier, not an ensemble, at least in deep learning. And okay, and this correspondence is we're going to be able to say that the thing on the left-hand side or approximates the thing on the right-hand side or vice versa. And this is going to allow us to port the theory from the ensemble methods to the individual classifier. Okay, so that was the introduction. The next thing I'm going to show you is some experiments, which are just going to suggest that actually this idea has some mileage. It's not a totally crazy thing to consider. Like actually, it's pretty promising. Then I'm going to take you through the setting in which where we're able to prove this correspondence. And finally, I'm going to tell you about some potential future applications of this idea. So the experiments. So what I mentioned is that when we train the single neural net as an approximation of the ensemble, the critical detail is that we need to maximize the margin of the neural network. So what does that mean? In a linear classifier, let's say we're doing binary classification with a linear classifier, the margin is the distance of the nearest training point to the decision boundary. We actually need to think about normalized margin because margin is not invariant to rescaling the weight vector or the input. So we care about normalized margin. For a deep network, we need to modify this definition slightly. So we can think again about margin as just the distance of the closest training point to the decision boundary. But the normalized margin of a deep network, we're going to have to modify the notion of norm that we consider to respect the deep compositional structure of the neural net. So here we're just taking a product of weight norms over the layers. So these are just notions of normalized margin. You might be familiar with normalized margin if you've ever looked at something like an SVM, but here we're generalizing the definition to a deep network. Okay, so the idea of our experiments is that we're going to train ensembles of neural networks to 100% training accuracy. So we're only going to consider things which completely fit the training set, but we're going to control the normalized margin of each ensemble member. And we're going to measure the effect that normalized margin has on test accuracy. So to do this, we create a technique called normalized margin control, which essentially carefully scales every aspect of the training process to control the normalized margin of the solution to the deep learning problem. So normalized margin control carefully scales. We choose a special loss function, which regresses to a particular output scaling of the, we fit labels to a carefully controlled output scale of A using a regression loss. We control the scale of the weights in the network by projected gradient descent to a particular like kind of hyperspherical constraint on each layer of the network. And we control the input scale just by doing data pre-processing. So we project the inputs to have a fixed scale. And if you follow this recipe, like, don't worry if the recipe doesn't make sense, but essentially the recipe targets, if you follow this recipe, you're targeting a normalized margin of A. So you'll get you'll train the neural net, you'll get a solution that fits the training data to 100% training accuracy, but you'll be able to control the normalized margin. We do this, and what we find is that, again, all the networks here get 100% training accuracy, but we find that here I'm plotting test accuracy against targeted margin, targeted normalized margin. We find that varying the normalized margin controls the test accuracy. We can take the test accuracy from chance at small normalized margin to good test accuracy. So this appears to be completely controlling the generalization performance of the network, this normalized margin parameter. And so the main point is that normalized margin, increasing normalized margin increases the test performance, even though the training accuracy is always 100%. But the very interesting thing here is that this is actually for individual neural networks. So we can think of this as an ensemble of size 1. Now we start averaging over multiple neural networks, and we get this behavior. So what we're finding is that if you want to improve test performance, instead of increasing normalized margin, alternatively, you could increase the ensemble size at small normalized margin. So this is the main experimental result, which I want to point out. Essentially, we're showing that there's an equivalence between training a single neural network to large normalized margin or training an ensemble of neural networks to small normalized margin and then averaging. So this is the main, this is the main idea of the talk being shown in this figure, that it actually seems to hold in practice for this binary classification problem. So with the experiments out of the way, I now want to show you, like, why did we even think to generate those plots? Like, what was the theoretical basis that we even thought to run these experiments? Also, what does it have to do with information theory and potentially algorithmic information theory? So the theory here, let me remind you of the definition of the base point machine, which is a single classifier that approximates the aggregated prediction of an ensemble of classifiers. And we have two main theoretical results. The first we're going to call concentration. So the claim is that if you condition on fitting a training set to 100% training accuracy, as you take the normalized margin to infinity, then the function space of an infinitely wide neural network actually concentrates on this base point machine. So we're proving the correspondence for infinitely wide neural networks, that, that we can actually get the entire function space of the network to concentrate on the approximation to the majority vote. The second result is the generalization result. So the claim is that base point machines have nice generalization properties. They inherit the generalization properties from the ensemble method. So I'm going to sketch the arguments that give you these results. And I'm going to focus on giving you the intuition. And if you want the kind of complete argument, you can look at the paper. So the sketch. The first thing that we show is a classic result. So this is a classic result. The function space of an infinitely wide neural network conditioned on fitting a training set is the posterior distribution of a Gaussian process. So this is referred to as the neural network Gaussian process correspondence. And then the interesting thing that we show is that if you suitably define the normalized margin of this neural network Gaussian process, if you consider what the normalized margin of the finite width network is, and then track it as you take the infinite width limit, what we show is that taking the normalized margin of the infinitely wide neural network to infinity causes the GP posterior distribution to concentrate on its mean. So to show you graphically what this means is that this represents the sort of posterior at a small normalized margin. And if we take the normalized margin to infinity, we get these functions to concentrate on the mean. So this is the picture of what's going on. The final step is to make the argument that the mean, which is what the infinite normalized margin network concentrates on, is actually an approximation to the majority vote. And for that, we use a result in convex geometry. So the observation is that you only need to make the argument for linear classifiers because an infinitely wide neural network has a kind of linear structure because it's in the kernel regime. So making the argument for linear classifiers, we have an ensemble of linear classifiers, which I represent with this oval. This ensemble has a center of mass. And then for any input corresponds to cutting this ensemble with a hyperplane, where the hyperplane corresponds to the input. And what we care about is the center of mass a good approximation to the majority? So for the side of the hyperplane, it may not be obvious why this is the right geometry of the problem, but you can look at the paper for more details. But essentially, what we care about is, does the side of the hyperplane the center of mass lies on contain the majority of the mass of the body or the minority of the mass of the body? We use a result called Grunbaum's inequality, which says that the probability of the half space of a convex body that contains the center of mass is actually at least 1/e, which is about 36%. So this is a sort of plausibility argument that the center of mass is a good approximation for the majority, although this is a slightly disappointing result because it's actually not saying that it's above 50%, which is what we would really want. But this is a kind of a nice result that was actually proved by people working in social choice theory who were interested in properties of electoral systems and when you can use a single voter to represent the beliefs of an electorate. So there's a kind of nice parallel between something that was interesting to social choice theorists, and then this thing that we care about, which is when can a single ensemble member approximate the majority decision of an entire ensemble. Anyway, so that was a sketch of the first result. The second result is that these things called Bayes point machines have nice generalization properties. And to argue this, we actually assembled a bunch of disparate results from the machine learning literature. So to explain this, I'm going to introduce a bit more theory. So given an ensemble of classifiers that I'll refer to as Q, we can classify a fresh test point X in two natural ways. The first is to pick a random ensemble member and then return the prediction of that random ensemble member. That's sometimes known as the Gibbs classifier. And the second way is the majority vote over the ensemble, which is also referred to as the Bayes classifier. And then what we show is that, okay, the test risk of the Bayes point machine is approximately the test risk of the majority vote. That's just by the definition of what the Bayes point machine is. It's an approximation to the majority vote. We then show that under certain conditions, this is actually much smaller than the expected risk of the randomized predictor. That uses, I'll tell you what result that is in a moment. And then finally, we use the Pack-Bayes bounds to bound the expected risk of the randomized predictor in terms of some information theoretic stuff. So the second inequality is known as the C-bounds, and the third inequality is the Pack-Bayes theorem. So let me just give you the summary of what this is saying. The left-hand side is the risk of the Bayes point machine, and then the right-hand side we ultimately derive is the Pack-Bayes bounds that takes the ratio of the number of bits needed to describe the ensemble divided by the number of training examples. This is important because an ensemble can be described much more efficiently than an individual member of the ensemble. So this is where, the information complexity of the ensemble can be much smaller than the dimension of the parameter space. For instance, if the ensemble fills the entire parameter space, then you can describe it with 0 bits, essentially. Whereas an individual ensemble member would, it takes the number of parameters. But essentially, this is, I can speak more about that at the end, but essentially this is a bound which relates the description complexity of an ensemble of classifiers and divides it by the number of training examples. And if that's small, then the average, then you kind of know that the Bayes point machine will generalize well.
Sorry, quick,
yeah, please.
Clarification. So this is not training, this is not much smaller, and then comes the inequality. So the risk of the BPM is directly smaller than the number of bits. Because I mean, if you have this strong inequality, right? But it would be a very loose bound.
Exactly. So this is one of the main things that we're pointing out, that the Bayes point machine can perform much better than a randomized predictor.
Yeah, but the bound is with respect to the Bayes point machine and not for the expected risk, right?
The right-hand side of the bound is on the expected risk. So this bound is actually going to be quite slack in comparison to this. And this is the right-hand side of this bound is what Ard Louis is speaking a lot about in his talk. So one of the main observations here is that that kind of analysis that we heard about yesterday can actually give you a very slack bound in comparison to the best possible classifier. I can speak a bit more about interpreting these bounds at the end of this time. So I want to speak a bit about like the outlook, why I'm excited about this direction. So we've kind of proposed this correspondence between individual classifiers and aggregated ensembles. It gives potentially a new way to understand generalization in deep learning. It's based on old ideas about kernel methods. And I have this kind of like, what's better than reading old papers? It's reading old textbooks. And I highly recommend reading this textbook on kernel methods by someone called Ralph Herbrich, who I just consider this book to be very, very good. And it seems to be not very well known. And this textbook develops this theory for kernel methods, essentially reporting the theory to neural networks. Another thing I want to point out is that we're using controlled optimization as a scientific tool. The observations in this talk came about from controlling this quantity called normalized margin. Often in deep learning, the optimization is sort of poorly understood, and then it's not really clear what matters for generalization. But we're observing that we can just control important properties and measure their effect. That we're charting the behavior of a function space that we do not fully understand, and optimization is actually our friend. It can help us understand it. And to give you the concrete example was this technique called normalized margin control that we developed to understand the dependence of generalization on normalized margin. I want to point out that I think that these ideas have a potential application to uncertainty quantification. Here we want to train an ensemble of neural networks and estimate the model uncertainty by considering the properties of this ensemble. But what we need to avoid is the ensemble collapsing onto a single function. And the claim is that if you're not careful, that's actually going to happen. And normalized margin control can be used to actually anti-regularize the ensemble to prevent the collapse. So the main thrust of this talk was arguing that by maximizing normalized margin, we can collapse the ensemble in a desirable way. And now what I'm pointing out is that we could actually anti-regularize, this would give us good generalization. We could anti-regularize the ensemble by making the normalized margin small, thus expanding the variance of the ensemble. And this can give us good uncertainty quantification, at least theoretically. So I think this is a potential application of these ideas more than just kind of like science of deep learning. So I want to thank my collaborators on this work, who I really enjoyed working with. And I've included here the links to the 2 papers that contain the ideas that I've talked about. This is the sort of key idea, this correspondence between ensembles and aggregating over ensembles and single classifiers. And I posted the slides on my website if you want to check them out. Thank you.
Slide, I mean, all speakers can send me the slides and I just put them on the website of the event. Yeah, that's why I reminded. Any other questions?
So you're saying that by playing with this margin, you can improve this generalization. So and I'm not sure if you mentioned this already, but have you, given that the neural networks are generalizing quite well, but how are you specifically controlling it? That means presumably they are already somehow.
Right. This is what we found is essentially it's quite difficult to actually train for small normalized margin. It requires very delicate optimization.
Okay.
So actually in my PhD thesis, I've been working on optimization methods for neural nets, which is, I think, partly why we were able to do this, because I'm not just using ADAM and SGD. I actually developed neural network optimizers tailored to neural networks, and they can do this kind of thing of like returning small normalized margin functions. Like that's a delicate procedure. If you just, the other comment is that people use cross entropy loss to train classifiers. That's a margin maximizing loss function. They also use weight decay, which makes the weight small. Both of these things have the effect of making the normalized margin large. So
the question is, do you understand? I mean, what is it about the neural net that is automatically giving you a reasonable? Or are you saying that it's just hard? It's hard to get it small, so automatically it's big or something like that?
Yeah, essentially, if you think about what needs to happen to get a small normalized margin function, you need to, if this is the decision boundary, you need to train the network to bring the training point very close to the decision boundary, but it can't cross. So if you're not careful, there's some noise in the training process that the point will jiggle across the decision boundary, so you'll get low training performance. So you need to be very careful to. So it's much easier actually to train to put the points far away from the decision boundary.
Can you go back to the one of the last parts, the correspondence to the uncertainty? Yeah. But from this slide, it almost looks like a kind of trade-off. Is that you expect that there is a kind of trade-off that either gets good generalization from an ensemble or good uncertainty estimates?
I think that there's not a trade-off, because if you had unlimited compute resources, you would rather form the ensemble then you can take the mean to get good generalization performance, or you can inspect the variance to get the uncertainty information. But if you're compute limited, which we are in practice, then you'd rather only train one neural network. So then you would prefer to be on the other side. But if you have unlimited resources, you would rather form the ensemble, get both the uncertainty and the generalization.
Right. But it seems like to get the good uncertainty bounds, you need a kind of ensemble of methods that are formed by themselves.
Right.
Each individually that methods. If you give them a larger margin, then yes.
That's what we're arguing, yeah.
I'm not sure I understood that. Can you turn this into an algorithm efficiently?
Yeah, we haven't actually experimented with this yet, but what we're proposing is, use this thing called normalized margin control and just train 10 neural networks to small normalized margin, measure the variance and the predictions. That's what we're proposing. People do deep ensembles at the moment, but they're not careful about which loss function they're using. They just use whatever they get off the shelf. And our claim is that is suboptimal, because if you're not careful, you can get this collapse happening.
Another question. Can you go back to slide 14?
Yeah.
So for you guys,
For a deep network, if you look in the function space of the network, then this space of solutions is an orthant. Essentially it's the region that correctly classifies the training set, which corresponds to getting the correct sign on every training example. So if you get the incorrect sign on one of the training examples, it's no longer a solution. That actually corresponds to an orthant of an n-dimensional space where n is the number of training examples. It may not be totally obvious, so I would encourage you to check out the paper. But essentially an orthant is a convex body, and also the density or the measure of solutions in this function space in the infinite width limit is a Gaussian distribution restricted to the orthant. And actually that's a setting where you can apply this Grunbaum's inequality, which is I also want to point out that this Grunbaum's inequality is a pessimistic result. Like you would more optimistically expect the mass of a half space that contains the center of mass to contain over 50% of the mass. But this is just, this is the result which always holds for kind of an arbitrarily bad convex body.
Thank you very much.
Thank you.